Of all the planets we know, ours is unique. The only one with water. We take it for granted, but without this magic liquid, life couldn't exist. Where our water comes from is one of science's greatest mysteries. From deep inside the Earth to the far reaches of space, the search begins for the source of our water. Earth is the only planet in the solar system with liquid water. 330 million cubic miles of it. It covers over 70% of the planet. It even makes up about 60% of our bodies. We know a lot about water, except where it comes from.
When we think about where Earth's water came from, it's not that simple, because we think that all the building blocks of Earth were probably completely dry.
If Earth forms without water, then where do our oceans come from?
It's a bit like a crime scene. The crime occurred a long time ago and the evidence has been tampered with. So it's very much like being a detective. You've got to look back in time to try and understand what was going on 4.5 billion years ago. It's a hard problem.
For the first time, scientists from different disciplines are working together to find the origin of Earth's water. The answer has the most amazing implications.
We know of no organism that does not require liquid water to live. And therefore, when we ask, how did a planet acquire its water? In essence, we're hinting at the question of what makes a planet able to support life.
In order to unravel this mystery, we must go back in time and look for clues at the birth of the solar system. 4.6 billion years ago, our sun is a newborn star, surrounded by a vast disk of gas and dust. Over millions of years, this disk of matter condenses to form the planets. Far from the sun, it's so cold, planets like Jupiter form with icy cores. Closer to the sun, it's more than 1,000 degrees hotter than it is today. Earth forms from substances that condense at high temperatures, like rock and iron. It's too hot for water. Earth is bone dry. For scientists, one possibility is that water was delivered by comets. From the frozen wastes of our outer solar system, they're mostly ice. Toby Owen has been studying comets for over 40 years.
As soon as people figured out that comets had a huge amount of ice in them, then it seemed reasonable that comets striking the Earth would have brought that ice with them, and so that ice could have melted and produced the oceans.
For 600 million years, the early Earth is bombarded by hundreds of millions of icy comets.
Comets are very primitive bodies. That's what makes them so especially interesting. The ice in comets is ice that has been untouched since the solar system formed.
So if comets brought all of Earth's water, then the water we drink, wash, and swim in fact, the water that makes up our bodies, is older than the planet itself, and is from the edge of the solar system. But the evidence is still circumstantial.
We need some clues to discover how the Earth got water. We need some clues in the water on the Earth that we can relate to other things, like comets, to see if we can decide what brought the water in.
Luckily, water contains the perfect clues. To the naked eye, water looks the same, but there are subtle differences depending on where it comes from. All water molecules are made of 1 part oxygen and 2 parts hydrogen. But the hydrogen comes in 2 forms. The bulk of hydrogen in water is normal or light, but a tiny fraction, the blue bits, are heavy hydrogen. The ratio of heavy to light tells scientists where the water comes from.
You and I, and all the animals, and all the trees, and all the oceans, and all the lakes, and the rivers on the Earth have the same ratio of heavy hydrogen to light hydrogen. That's our water. That's the water of the Earth. So the question is, what is that ratio like in the kinds of objects that could bring the water to the Earth?
To find the ratio of heavy to light hydrogen in the water on a comet, scientists need to get a sample. Easier said than done.
One of the things that made people so interested in comets is that they're completely different from anything else in the sky. Suddenly, from nowhere, this huge bright object appears and moves through the sky and then disappears again.
Because astronomers never know when they'll show up, most comets are out of reach.
You'd have to keep a spacecraft in your garage, something like that, ready to go at any minute when one of those comets appears.
But one comet has a special place in astronomers' hearts. It's not the biggest or the brightest, but it is predictable.
Halley's Comet is special because it's a big comet, and still it is one whose orbit we know. So that means we can predict when it's coming back to the Earth. We can make that prediction very well.
In 1986, Halley was once again within reach, close enough to grab a sample. For Dr. Carey Liss, just seeing Halley's Comet was the chance of a lifetime.
I actually was excited about Halley's Comet, and at 1 in the morning we were out there looking out in the sky, and I remember to this day we saw Halley's Comet really nicely, and that was very inspirational to me.
Because scientists knew where Halley would be, they could build a space probe for a rendezvous. The probe Giotto was designed to fly through Halley's tail.
One of the most exciting things that Halley gave us was not just here's a comet, here's what a comet looks like, here's the structure, but we could start doing chemistry. We could start understanding the composition of the comet.
Finally, scientists can analyze comet water and discover if it's the same as the water on Earth. On March 13th, 1986, after traveling for 8 months, Giotto enters the tail of Halley's Comet. Then a crisis. Giotto hits a large particle of dust, traveling at 42 miles per second. Communications with the probe are intermittent.
There was a tense moment there when people thought the whole thing might be lost.
32 minutes later, communications are restored. The probe samples the water vapor in Halley's tail and sends the data back to mission control. Astronomers are about to find out if the water on a comet is the same as the water on Earth. But when the results come back, the mystery only deepens.
And what we discovered, to our surprise, was that the hydrogen in the cometary water was about twice as massive as the hydrogen in water on the Earth.
With twice as much heavy hydrogen, the water on Halley's Comet is not the same as the water on Earth. While it looks, tastes, and behaves just like Earth's water, to scientists, this difference is crucial. It can only mean one thing. Comets can't have brought all of Earth's water.
Well, that's a big, exciting result. It kind of defeats this lovely idea that comets brought all the water to the Earth.
In terms of did comets bring water to the Earth, it was a revolution and a change. And that's pretty exciting.
For years, scientists thought that comets were the source of all the Earth's water. But the evidence now makes this impossible.
So that was a very exciting result because it meant that you had to have some other source of water to produce the oceans that we see. And now we were going to have to go through the excitement of trying to figure out what really happened.
In 2002, a chance discovery suggests the answer might be closer to home. When the Earth first forms 4.5 billion years ago, it's too hot to form with water. But the planet has water now. If it wasn't delivered by comets, then has it been here all along? To find out where the water comes from, Professor Stephen Moyges is looking for clues to when it first appears. As a geologist, he uncovers the planet's past by looking at its rocks. But the past has a big hole. It's called the Hadean, or Dark Period, because nobody knows anything about it.
The problem of the first 500 million years of Earth history for geologists has always been that you have a nightmare scenario where you don't have any rocks or minerals to investigate.
It's thought early Earth is a fireball of molten rock, but with no evidence from this time, it's just a theory. Then in 2002, Moyges makes an earth-shaking discovery: the oldest mineral sample ever found on our planet, a crystal of zircon. Locked inside these tiny grains is a vital clue. Chemical analysis of zircon crystals reveals whether they formed in the presence of water. Over 7 years, Moyges finds and dates nearly 100,000 crystals of zircon. One stands alone.
The oldest one that we've found so far is 4.38 billion years old. Now, I'd like that to sink in.
When this crystal was made, the Earth was just 180 million years old. If this line represents the age of the Earth, then the dinosaurs died out here. Rewind about 4 billion years to the end of the Dark Period. The zircon crystal was formed here.
We're talking about time spans that are beyond comprehension. So for instance, in this rock here, there are zircon crystals that are 1/3 of the age of the universe. So these things have been around for almost as long as the Earth has been a planet. Talk about time capsules.
Analysis shows this 4.4 billion year old zircon crystal forms in liquid water. Rather than a dry planet, the crystal reveals that early Earth already has water on its surface.
When we made the discovery, that was very, very exciting because it wasn't fulfilling a hunch. It was true discovery. We didn't know what we would find.
For years, scientists thought that planet Earth forms dry. Moyges' discovery means that theory is wrong. Professor Mike Drake is searching for a new theory about how the early Earth forms wet.
Now, zircons tell you for sure when liquid water had to be present, and that's at about 4.4 billion years ago. And all of a sudden, we don't know where it came from. We've suddenly got a major problem. We have to seriously consider the possibility that water was present in the building blocks of the planet as it formed.
But how could water exist in the building blocks if the blocks were boiling hot? The answer requires another step back in time.
I finally went back to what the system looked like 4.5 billion years ago before there were any planets, and realized we had these fine grains of dust embedded in a sea of hydrogen and helium and oxygen, and some of the hydrogen and oxygen reacted to make water. So we basically had dust surrounded by water.
Over millions of years, the dust and gas condenses to form the planets in the solar system. Far from the sun, Jupiter and Saturn form with icy cores. But ice isn't the only way planets can lock in water. Further in, where it's too hot for ice, water can be locked into rocks, as this mineral demonstrates.
If you look at it, it looks really dry. If you touch it with your fingers, it's really dry.
But heat unlocks its secret.
And now you can start to see it's really boiling up into little balls of water. There's a huge amount of water coming off of this mineral. So a perfectly dry-looking mineral can contain a huge amount of water.
When the solar system first forms, the massive cloud of gas and dust traps the heat of the young sun. Where Earth forms, it's well over 1,000 degrees Fahrenheit. Too hot for such water-bearing rocks to form and build the planet. Yet soon after its creation, Earth manages to get water. Drake asks himself a new question. What if the early Earth traps water another way? A way nobody ever imagined.
One day I was drinking a nice cold drink, and I looked at the glass, and it had condensation on the outside of it, like this one does. You can see the water vapor on the inside if I run my finger around it. And I wondered if the same kind of process could have occurred in the disk around the sun 4.5 billion years ago. Could water have condensed out onto grains, much like it has onto this cold glass?
It's completely different to water-bearing rocks. If water vapor sticks to the grains of dust that build the planet, they could be the source of the oceans. An entirely new way for planets to form with water. He tests the theory with one of the main ingredients of planet Earth.
The green mineral in this rock is olivine, and olivine is the most abundant mineral that you find in the rocky planets. It's also the mineral that was abundant in the disk around the young sun 4.5 billion years ago.
He wonders if all the grains of olivine that form the planet have water stuck to them. He uses a computer to calculate the interaction between olivine grains and water vapor in the very early solar system. Water molecules stick to the olivine crystals.
So 30 grams of olivine allows me to absorb about 0.3 milliliters of water.
But can you capture enough water to fill the oceans? Drake has to scale up his calculations. How much water could stick to an Earth-sized pile of olivine grains?
Frankly, when we started these calculations, we didn't have a clue about how much water we could absorb. And we were actually astonished when we discovered we could get 10 times the amount of water that's currently in the Earth's oceans.
Professor Drake believes as the early Earth forms, it already has billions and billions of gallons of water. Water that sticks to the trillions of grains of dust that build the planet.
It's really exciting to have come up with a new solution to one of the most fascinating and important questions that humans face, and that is, why do we have any water? Because without water, we cannot exist.
But Drake's theory is new, and not everybody's buying it. It has a flaw even he can't explain. The type of water. Our water has a signature. The ratio of heavy to light hydrogen in the Earth's water tells you where it comes from. The source of Earth's water should have a matching signature. But the water that condenses directly from the disk of gas and dust around our young sun is very different. It would look and taste the same as Earth's water, but it would have 6 times less heavy hydrogen.
Now, I don't mean to pretend that we've got the entire answer yet, and until we can show we can get the right ratio of heavy to light hydrogen, we cannot be certain that this process is responsible for the Earth's oceans.
If Earth's water doesn't come from the building blocks that form the planet, and it doesn't come from comets, where does it come from? Professor Alessandro Morbidelli has developed his own theory.
All of a sudden, everything fits together. And you feel you understand a piece of your past that nobody was there to observe.
Are the origins of Earth's water finally about to be revealed? The origin of Earth's water is one of the biggest mysteries in science today. Scientists are looking for a match. There must be somewhere in space that has the same kind of water as Earth. The answer may be locked inside this lump of rock and metal. Few people know more about these meteorites than Gary Huss.
Well, I grew up in the basement of a meteorite museum my grandfather had in Arizona. And so I'd go up and look around at the meteorites, and by the time I was 2, I knew all of their names. Once you get bit by a bug like that, you can't get rid of it.
While comets are made of ice and dust and come from the cold fringes of the solar system, a meteorite comes from somewhere else. Orbiting the sun between Mars and Jupiter are millions of lumps of rock and metal called asteroids. Some 200 miles across, weighing millions of tons. Leftovers from the formation of the planets. Sometimes asteroids collide, and fragments fall to Earth as meteorites. But what can they tell us about the origin of Earth's water?
The initial idea 100 years ago was that you had a major planet and it broke up and everything was dry and hot.
Looking at meteorites under a microscope reveals a different picture.
As we learn more about meteorites, it turns out that some of them are actually quite wet, a few percent water.
This is a slice of a meteorite, known as a carbonaceous chondrite. The bulk of it, the black stuff, is a mineral with water locked inside. This fragment of rock was once part of an asteroid that formed 200 million miles away. It reveals that at this distance from the sun, asteroids formed with water locked inside.
There's water in the asteroid belt, and it's apparently always been there. We just didn't know how to recognize it.
Is there any water in the asteroid belt identical to water on Earth? To find out, Professor Huss measures the ratio of heavy to light hydrogen in the water-bearing meteorites. He can do this with an ion microprobe.
We were actually quite fortunate to get one of the very first of this newest generation of ion microprobe.
The machine fires a beam of charged particles at the meteorite. This expels all the hydrogen atoms in the water. The heavy hydrogen and normal hydrogen are then separated so he can measure the ratio between them. What Dr. Huss finds looks like a crucial piece of the puzzle. The ratio of heavy to light hydrogen in the water in asteroids varies. But some have exactly the same ratio as the water on Earth. It looks like scientists have finally found where Earth's water comes from.
So then the question is, how do the two things from different parts of the solar system end up with the same kind of water?
Chemistry can't solve the conundrum. But mathematician Alessandro Morbidelli has a radical theory that could explain how water from the asteroid belt ended up on Earth.
The idea was driven really by measurements, by the fact that the water on Earth is so similar to the water that we get from meteorites that come from the asteroid belt.
Morbidelli took a revolutionary look at an old subject, how the planets in our solar system were built. Before, scientists looked at the formation of the 4 planets closest to the sun. They studied how matter near the sun condensed into bigger bodies, eventually forming the planets Mercury, Mars, Venus, and Earth. Morbidelli has done something radically different. He's the first scientist to look at the formation of all 8 planets in the solar system as a whole. From Mercury, closest to the sun, to Neptune, 80 times farther out.
The solar system is entirely interconnected, and we cannot study the formation of a portion of the solar system neglecting the other regions of the same system.
You can't study the planets in isolation because they're all linked by one force.
The only force that matters is actually gravity. So these things are relatively simple. We don't need to invoke strange physics or strange forces or dark matter.
As the planets grow, they interact because of gravity. Morbidelli recreates this interaction with a computer model, giving him a ringside seat at the birth of the solar system. About 1 million years after the birth of the Sun, the disk of gas and dust in the inner solar system condenses to form about 50 mini-planets. During the next stage, these mini-planets collide and form bigger planets. This demonstration shows what happens. The oranges represent mini-planets near the Sun. It's too hot for them to form with water trapped inside. As you move out, it gets colder. 230 million miles from the Sun, it's cool enough for mini-planets to form with water-bearing rocks. Green vegetables represent mini-planets with water.
The Earth eventually will have to form in this region, so in a region which is very hot, where nominally there should be no water.
If you look at the mini-planets close to the Sun, Earth forms from local material.
The mini-planets orbit around the Sun on trajectories which are almost parallel, like this.
Mini-planets collide to form the Earth. It forms from dry material.
But in this case, the Earth, because it formed from mini-planets which were dry, will also be very dry. Luckily for us, this is not what happened, so we need to revise our model.
Because Morbidelli looks at the solar system as a whole, the whole scenario changes. Enter a new player, Jupiter. Jupiter is the biggest planet in the solar system and one of the first to reach full size. It's 300 times more massive than Earth. And in the early days of the solar system, it's starting to throw its weight around. Represented by this silver ball, Jupiter's massive gravity disrupts the orbits of the mini-planets.
Now, the mini-planets, in particular those farther out, have a more irregular motion, and in this way, the mini-planets can mix with each other.
Earth now forms wet. Look at the formation of all 8 planets at once, and Earth forms from a mix of mini-planets, some dry, some wet. This model explains how Earth came to have similar water to that found in the asteroid belt.
All of a sudden, everything fits together. And you feel you understand a piece of your past that nobody was there to observe. These moments are fantastic. There are just a few moments like that in a career of a scientist. But even if it happens once every few years, those moments are so exciting that they are worth years of work.
Morbidelli's idea is now the leading theory of how Earth got its water. But it's not the whole story.
For the moment, it is the best answer that we have. But as we say, the devil is in the details. There are certainly some details we don't understand, so we need to keep working until we understand all of them.
The question is, what happens to the water on Earth during the continuing collisions with mini-planets the size of the Moon and Mars?
The energy of this collision is so high that it's capable of melting the entire Earth. In addition, it actually vaporizes some fraction of the Earth's rock.
If these collisions vaporize rock, how can the water survive? The origin of Earth's water remains unclear. Scientists have theories that can get the water to Earth, but can they keep it here? The final stage of Earth's formation is a series of cataclysmic collisions. Can water survive the process? The answer is in the night sky. Robin Canup has been working on the formation of the moon for 13 years.
I think people are particularly fascinated by our moon because it's been our companion throughout all of human history and throughout all of the Earth's history. Every human that has lived has gazed upon the same moon.
The moon was formed by a collision between the early Earth and a mini-planet.
The leading idea for how the moon formed is known as the giant impact theory. Just as the Earth was finishing its formation, the Earth experienced a collision with another planet-sized object, something that was smaller than the Earth, but still comparable to the current planet Mars in its size. So this was an enormous collision.
The last of several giant collisions between mini-planets that form the Earth. Why does this collision result in a dry moon and not a bigger Earth? Robin has developed a computer model to find out. The key turns out to be the angle of impact.
When this collision first comes in, it's at an oblique angle. The impacting planet is sheared apart into this long arm of debris that then wraps around the Earth to form a disk.
In no more than the span of a human lifetime, the disk of debris condenses and forms the moon. So why isn't the moon wet?
If you distribute that rock out into a disk around the Earth so that the disk is very spread out and there's a lot of surface area over which that rock can lose its water, then the water will tend to evaporate and be lost.
The model explains why the moon is dry, but it doesn't explain what happens to the water on Earth.
The moon-forming impact is an event of such a scale that it's almost difficult to comprehend. If you've ever visited a volcano and seen the molten lava coming out of the Earth, that's what we mean by molten rock. That would have been the coolest material on the Earth after this impact. If you continue to heat that material even more, it will eventually actually vaporize. The moon-forming impact was energetic enough to do both.
These cataclysmic impacts should have driven off any water on Earth. The impact occurred about 4.5 billion years ago. And as this is the last cataclysmic collision that planet Earth suffers, the date is vital. Professor Moiges' zircons reveals Earth has water 4.4 billion years ago, very soon after the collision that formed the moon. If the collision had blasted Earth's water into space, where did the water in the zircons come from?
Since water was present here in liquid form and abundantly very early on and soon after the moon-forming event, it means that either the water was delivered very rapidly right after the moon formed, which I think is highly unlikely, or water was already present on or within the Earth before the giant impact that resulted in the formation of the moon.
So the Earth's water survives this last cataclysmic process of planet formation. But how? Professor Drake thinks the water has been here from the start. He has a theory about how it survives.
So the collision of a Mars-sized object with the Earth is an incredibly violent event. It'll melt the Earth. Now, the obvious question is, if the Earth went through such a violent event, how did it manage to keep its water? Most people think that if you heat something up, you boil all the water off, but that's not actually true. Any water that was in the Earth will be dissolved into that molten rock. That molten rock or magma is literally a sponge for water. You can dissolve vast amounts of water in liquid rock.
The early Earth is a giant fireball of molten rock. Dissolved inside are billions of gallons of water. But how does this rock become our blue planet?
This red-hot molten Earth is going to have lots of water in it. And that water's got to go somewhere when the planet cools down.
The rocks in this Arizona desert reveal what happens as the cooling rocks solidify.
The rock that crystallizes deep inside the planet will have the water kept in the minerals that crystallize. Here we have some micas. This happens to be a granite. And that water will be kept in the planet for 4.5 billion years.
Rocks that solidify deep in molten lava can hold water. But lava near the surface forms a different type of rock.
Any rock close to the surface, this one, for example, right here, you can see the holes in it, is going to lose its water. It's going to make little bubbles, which is what these holes are. Now imagine that there was rock like this all over the planet crystallizing. Water gets out into the atmosphere. Just look at the mountain range behind me and imagine the amount of hot, steamy water that could be coming out of these rocks as they crystallized.
All over the planet, water vapor escapes from the cooling rock. Earth's atmosphere is dense with steam. 100 million years after the impact that formed the moon, Earth has cooled enough to form a crust.
And you'll have boiling hot rain coming down onto the surface of the planet, running down in rivers, and eventually making the oceans.
But the story is still missing a chapter. Many scientists believe Earth has more than one source of water. Where did all of Earth's water come from? According to the leading theory, water arrived when mini-planets from farther out in the solar system collided with the early Earth. But scientists suspect this isn't the whole story.
I personally think there's more than one way to get the water to the Earth.
Like comets. Analysis of comets shows they couldn't be the source of all our water.
We can be pretty sure that comets must have brought in some of the water, because we know comets must have hit the Earth. But the question is, how much? What is the fraction that they contributed?
The solar system may have furnished another source of water.
We've been hit by comets and asteroids, and some of the water may have come from there. But for me, it's a no-brainer. At least some, if not most, of Earth's water had to come from absorption of water under grains before the planet ever formed.
But did these different sources bring enough water to Earth to support life? It's now impossible to work out how much of Earth's water comes from which source, because the water has been mixing for over 4 billion years. And over all that time, Earth's water has not only mixed, but changed.
The Earth's oceans basically have gone through a lot of processes since the Earth formed. There's rain and snow, and all of these things have caused the composition of the water to change a little bit.
By how much the water has changed, nobody knows. But there's a place where we might find out. A volcanic island chain in the middle of the Pacific. On the Big Island, Hawaii, Dr. Gary Huss is searching for the oldest water on Earth.
The Hawaiian Islands volcano is basically what's known as a hot spot.
A place where lava steadily oozes from the Earth.
The rocks that we're standing on in the Hawaiian Islands come from the very deepest part of the mantle of the Earth, thousands of miles below the surface. And it provides us a sample of material we could never get any other way.
When he looks at water locked in rocks drilled on Hawaii, Huss is actually looking at water from the middle of the Earth. Water unchanged since day one.
If you want to look at what the composition of the water on Earth is at the time that the Earth formed, this is about the only place you can look.
Can Huss find evidence that there's primordial water deep inside the planet?
Oh, it's one of these guys? Oh, that's neat.
His approach is unprecedented, and early results suggest he might be onto something.
Well, this is good. This is a great sample for your purpose.
When we first found the hints, we definitely got excited about it. It does look like the water from deep in the Earth is different from the oceans, and it's different significantly.
So different, it could be primordial water, untouched since the birth of the planet. This research could ultimately deliver extraordinary answers to the question of the origin of Earth's water. And Hawaii isn't the only test site. The team is also sampling water from another hotspot, Iceland.
If we can nail this down for, say, the Hawaiian volcano, and then we can go to the Iceland hotspot and we get a different answer. Not only now do we have differences between the deep water and the surface water, we've got differences between a volcano on this side of the Earth and a volcano on that side of the Earth. There may be evidence for more than one source at this point.
One day, deep inside the planet, they may find reservoirs of primordial water different from each other. Such a discovery would mean one thing. Our water must have different origins. The implications are profound. For years, astronomers have been working toward one goal: scouring the skies in search of another planet like Earth. A rocky planet, just the right size and just the right temperature for liquid water and life.
We know now of 250 other systems that have planets in them, and we haven't found an Earth yet.
Billions of systems are yet to be explored, so the numbers are on your side if you're looking for another Earth.
We have 100 billion stars in our galaxy. Of them, we think about 10%, so 1 in 10 is a sun-like star. And we think that maybe 1 in 10 of those stars has planets. So that's about 1 billion stars in our own galaxy we think would have an Earth-like planet in it. Now, whether it has water on it is a different story.
Do any Earth-like planets out there have water? Could any support life? Today's telescopes can't answer that question, but computer models can. Dr. Sean Raymond has devised one.
We take our cues from observers. So with telescopes, people go out and find giant planets orbiting other stars. Then we take the orbits of those giant planets and try to figure out, in that system, could you still form a planet like Earth?
Raymond's computer model shows as planetary systems form around stars, some Earth-like planets end up with water.
We're modeling the formation of a planetary system here. All this red stuff is dry, the blue stuff is wet.
He starts with lots of mini-planets. Far from their sun, the blue ones have water. Closer in, where it's hotter, the red ones form dry. As the planets form, they start to cool. Like Earth, any planet warm enough to have water must orbit in the dry zone.
This guy right here is going to end up being a pretty good Earth analog.
The model shows how wet mini-planets from further out are pulled in to collide with a mini-planet in the dry zone, like Earth.
And there you just saw it turn from red to yellow to green. That's water delivery happening right there. And by the end of this particular simulation, it's very wet.
The result is a planet in just the right place for water, another Earth. Using the model, Raymond can calculate what's needed to form other Earths and how many there might be.
And we say, what if things were a little bit different, like we think they are around this other star? How would that affect the formation of planets like Earth, and how would it affect water delivery to those planets?
If Earth's water was delivered in more than one way, via comets, and with water as one of its initial ingredients, suddenly, the chances of finding an Earth-like planet with liquid water have just shot up. So too have the chances of finding alien life.
This is a big deal because are we alone in the universe, right? No one knows for sure. Everyone's excited about life on other planets. And what we're doing is one step towards trying to find life on those planets. It's really cool. I mean, it's very exciting.
And because scientists now think planets can get water more than one way, they're more confident than ever about the answer.
When people ask me if there's life out there, I say yes. And is there life like we know it, with a rocky planet where water has been brought to it? I think the answer again would be yes.
So by finding out how Earth got its water, we can find out how likely it is that out there somewhere, maybe millions of light years away, there are other alien forms of life.
Imagine the power of still photographic images. Moments frozen in time that can change the way we perceive our place in the world. To the ends of the earth isn't a new concept. It began when people first started looking beyond the next ridge, the next valley, to the lands beyond the mountains. They searched for the unknown, the unexpected, the surprising, to map, catalog, and show to others. Each explorer searched in their own way to push boundaries, expanding and sharing knowledge of what existed in the great beyond. Here you will see through a photographic vision a story for the ends of the earth, photographs by Todd Gustafson, a lifelong personal search for the dramatic and the unexpected. Traveling the world for decades, capturing intimate natural history moments and dramatic wildlife action, Todd has brought to the viewer images from East Africa, Brazil, Namibia, Patagonia, Rwanda, the Galapagos Islands, India, Costa Rica, Madagascar, and the ocean realm, revealing common threads that exist between humanity and the natural world that forever bind our fates together. Ancient map makers could only present what they knew. Beyond the edge of the map was the unknown, inhabited by monsters and dragons. Todd still pursues dragons in his personal search for the ends of the earth. Through Todd's lens, we see a vanishing natural world. We can see a world we have the power to protect. We have a collective voice that can change the course of destruction to one of stability and rebirth. To the Ends of the Earth is more than a magnificent collection of wildlife photos. Todd's photographs allow us to experience vicariously the very behaviors people most want to see.
We live on the water planet, a world that is 70% covered by water. And the oceans hold about 96% of that water, indispensable water that maintains global climate and provides life-giving precipitation that sustains all living things. The very reason I'm a photographer and travel the world documenting the Earth's beauty is because my biology-zoology-trained dad took our family to Tanganyika's Indian Ocean beaches when he had time off from teaching. There was a string of beaches I remember vividly: Tanga Beach Club, Kigombe Beach, and Pangani. I remember swimming in the waves with my brother and sister, but most of all, there was Dad, pacing the beach, head down at low tide looking for seashells. He dug in the sand, turned over rocks, explored tide pools, and followed shell trails in the quiet shallows. There, he showed me how different shells lived in lagoons, tide pools, mudflats, and sandbanks of the Indian Ocean. Coronata shells leave a classic trail when they prowl the tidal flats for nutrients. When the tide changes, they bury themselves till the next low tide. Mollusks have different diets, which determine what style of locomotion each species evolves. Conchs have an amazing foot with a stylized operculum or trap door that allows them to vault across mudflats. They also have eye stalks that give them a wide angle of view. Another unique form of locomotion is employed by Janthena snails. They are pelagic, meaning they live in the open ocean, kept afloat by secreting from its foot a frothy liquid that hardens on contact with seawater into a raft of bubbles. This one has a colony of tag-along barnacles that filter ocean water as the shell travels the sea. A classic Indo-Pacific shell is the gold ringer cowrie. They're herbivores that feast on seagrasses and are commonly found empty on the beach. While the shell itself is beautiful, a living animal is much more intriguing. What you see here is the living mantle that covers the glossy shell. This thin membrane secretes calcium and creates that shell. This amazing creature is a nudibranch, a shellless mollusk that searches the coral reefs for food. When they eat stinging corals, the poison is stored in the feathery projections on its back. This makes him unpalatable for other predators. The gelatinous spiral of a nudibranch egg mass is a work of art. I think my favorite sea creature may be the sea hare. There are many different species, but I love the patterns on this one. Look at the surface and the electric blue dots. Here are some seashells found on a low-tide reef where there are no tourists. Seashells are abundant, and in this ocean documentary, I will suggest that people look at them, enjoy them, and leave them on the beach and in the tide pools where hermit crabs can use them as a home. With over 70% of this Earth covered by oceans, it becomes a real issue to try and find the spot that you think would tell the story that's beneath the water. Here in the Maldives, we have a lot of the elements that we need to tell that story. We have tropical atolls, we have lagoons, we have open ocean, we have really good access, and the life that is here, the beautiful Indo-Pacific life includes whale sharks. It includes manta rays. It's got powder blue tangs and sea anemones and clownfish and turtles and eels and octopus. It has the whole story. There are beautiful areas of untouched, undamaged reef that have beauty for as far as you can swim, as far as you can see. And even parts that were damaged during El Nino, they're showing new growth. So there's new coral, and it's marked by sort of a bluish tinge as the new coral is growing where the old ones were. The Maldives are one of the classic places in the planet to see whale sharks. And one of our goals, whale sharks. After searching this vast ocean, there was a whale shark. We jumped into the water and I actually bit through the mouthpiece of my snorkel. It was such an amazing surprise. Following whale sharks is extraordinarily difficult. With one swish of their tail, can be 100 meters farther from you than they were. So it's not good to follow them. Trying to get in front of them and just wait. Or finding a turn where you might be in front of them after that turn, that's the key. And then the question is, do you follow them as they go? Or do you just stay still and let them move through the frame with their great girth and the swish of that tail? As a safari photographer, I am used to grabbing my equipment, pushing the button that I know is going to make a difference in the shot, whether it's making it brighter or darker, or the focus, or any number of adjustments I could make. Underwater, there are housings that hold the same camera, and they have buttons that will control all of those functions, in theory. But when a whale shark or a manta ray is swimming at seemingly 100 miles an hour, it's difficult to find exactly the right button to make that thing happen. So that's a real challenge. We're using an underwater housing for our on-land cameras. So we're using a fisheye lens to get wide. Whale sharks are big, so wide angle is good. That wide angle fits into a domed port that makes all of the focus underwater very, very sharp. Here's the back panel allowing us to access all of the buttons and functions of the camera. Right now, I'm using this fan to make sure everything is dry and cool for the next time we go into the water with this housing. When filming whale sharks, it's different than photographing whale sharks. If you point the camera at a whale shark that's underwater and you take a picture, you either get it all in the frame or you don't. But when you're filming, you're trying to tell a story of the girth or the power or the size, the shape, the texture of this whale shark. So as the whale shark turned and I was filming, he came directly under me. It was a question, do I try to paddle and keep up, knowing that I can't? Or I filmed the head and held my position as he went underneath the camera, the entire length of his 20-foot body, till the tail did its last swish. I knew I was in. I know a lot of people think that in order to film or photograph underwater, you have to dive. And I can see the merits of diving. You can stay down longer and you can be a little bit more still. However, I don't dive, I snorkel. So everything you see in this footage will be from snorkeling. I feel you have the best access and the best light on that first 10 feet of water. A classic Pacific character in our story would be the giant clam. So when you say giant clam and you see a little clam 2 inches long with a little wavy, colorful lip, you think, wow, that's pretty, and you get a nice shot. Then you find one that's maybe 10 inches. Then you find one that's 16 inches, every single one of them having a different color, from blue to beige to green to black to turquoise, with stripes and spots. They are amazing. And what about sea stars in their varied colors, shapes, and textures? Turtles are cool. Here we have hawksbill turtles. We swam with 3 or 4 individuals, simply observing them as they picked through the seaweeds and grasses for nutrients. They come to the surface to breathe. Sometimes they're at the surface simply to breathe. Other times they're sighting or smelling to see where they are and where they want to be. My favorite shots are not when they're on the bottom. There's a lot of rubble and old-growth coral that makes distracting textures. But when they come up for a breath and they have the deep blue of the great beyond behind them, that's what I like. As with all photography, underwater photography is storytelling. You can take a picture of a fish. It can be sharp. It can be in the middle of the frame. It can be perfectly in focus. But if it's not doing anything, it's not a story. There's a picture of a parrotfish. It's pretty. The colors are dramatic. However, if there's a cleaner wrasse who's working on that fish, and if that fish were to twist and turn toward the camera, showing its teeth, with which it creates all of the sand in the ocean, that's a story. In India, there is a syndrome called tiger fever. It's just what I call it. If I haven't seen a tiger within the last 20 minutes, there's something wrong, and I get jumpy. Gotta have tigers. If you miss tigers for a day, it's a thing. If it's 2 days, it's a tragedy. Now, in the ocean, in this vast, limitless space of ocean, we were looking for manta rays. That was our goal, that was our quest. We needed to be strong. We didn't find manta rays, and it was a hard thing. It was really difficult. So we tried the next day, thinking, we're never gonna find manta rays. This is crazy. We tried once, we're not gonna do it. There they were. We got in the water, there were 6 manta rays on a fairly shallow lagoon. It was 40 feet, but wow, when you saw 6 manta rays swimming and going in circles around each other and doing these social behaviors that they do, heart-stopping, and it was as if we had scored a victory. As on land, photographing underwater at eye level gives the subject more power and resonates more with the viewer. This Indian bulb anemone is right at eye level and brings us into the striped clownfish's world. They stay safe inside the poisonous tentacles by developing a resistance to that anemone's poison and covering themselves with it as they swim and nestle in the tentacles. These photos further illustrate that point. Needless to say, underwater we are not in a vehicle as we are in a safari. If the cheetahs are here, we want to move to here and we can get the shot we need. If we're underwater, this just in, fish can really move quickly. And if you look like you're chasing them, they'll continually move away from you. I find that if there's subject matter in this area, there's dramatic fish, there's pretty stuff, just wait. Let them do what they're going to do, and pretty soon you'll have fish that are looking in your direction, fish that are absolutely parallel with your lens. You'll have some beautiful behaviors that you won't get if you're chasing. What I truly love about the tropical atoll that we are on is it's surrounded by a golden beach. And right at that shoreline in the golden beach are small fry. There are millions and millions of tiny fish in schools all around the island. They support gray herons that come and fish. They support the reef fish that come in and try and catch a meal. Even sharks. So black-tipped sharks at first light come through the shallows, and you can see the fish they make a split as that shark comes through. And when the bully boys from the ocean come in, there was one moment that I will never forget. Thousands and thousands of fish jumping 3 or 4 feet out of the water in a 50-foot wave as the shark was trying to eat. You can't really talk about oceans without looking at waves. These amazing phenomena are the result of water molecules traveling in circles via kinetic energy. The water of the ocean isn't moving much. It's energy traveling through the water that is in motion. The more energy, the bigger the wave. Columns of water are affected by the orbital energy. As the wave approaches the shore, the column is compressed against the ocean floor, causing the wave to rise up and eventually crest and collapse. When you are looking for turtles, you may find turtles. If you don't find turtles, there's always something else. Today we had cuttlefish. We had conch shells. We had beautiful flounder scooting amongst the seagrass onto rocks and changing colors along the way. Stingrays patrol the sand flats of the Caribbean. In Grand Cayman, we have a species of stingray called the southern stingray. And they grow especially big in the North Sound, where there's plenty of squid to eat. And they are looking for squid. They're also looking for murex shells or bivalves to crush with their bite plates. So sometimes if you'll see stingrays clustering, somebody's found something to eat and other ones want that food. Underwater, as on land, light direction and quality are crucial. You can see this in two different shots of stingrays. One is with soft muted light on a cloudy morning. Another is bright, sparkly light that's coming through and creating dappled patterns on the stingrays. I feel it's a little harsh. The last day was early morning, soft light, soft dappling, and really highlighted stingrays. You'll see the difference. So when we got on the water with the stingrays, I realized that the light angle was really important. If we became really focused on the species of stingray is what we need to get. It didn't matter what they were on, we were just going to get stingray. We realized that the pictures weren't all that good. The film wasn't all that spectacular. What were the stingrays doing, and where were they doing it? Was it shallow water? Was it clear water? Was it a clean, white, sandy ocean bottom with a clear ocean top? Or maybe there was a spray of seagrass behind them that added some depth and dimension. Were they swooping? Were they in groups? Or were they just a cluster of fins and tails? It all makes a difference in the final picture of the stingray. After the experience of day 1 and day 2, I knew what to pre-visualize for day 3. I wanted some of the grass flats along with the sand. I wanted the stingrays spinning into the shot, not a static going across the frame, spinning into the shot. And having the small reef jacks, having these silverfish right under them was cool too. Shallow Caribbean waters produce tons of sea life. Dramatic things like turtles, tiny things like seashells or sea fans. My favorite seashell might be the flamingo tongue. Coral life in the Caribbean is completely different than coral life in the Indo-Pacific region. Here we have brain corals for hard corals. We have elkhorn corals, staghorn corals for the hard corals. But the predominant things you'll see on the reef, the textural beauty of the reef, is created by gorgonians, sea whips, and sea fans that come in a multitude of colors: cream, brown, blue, purple, yellow, orange, all creating a tapestry in this Caribbean reef. Photographing and filming one sea fan or one beautiful gorgonian has its place. But when you have the gorgonians stacked up and mixed with sea fans and sea whips to create that tapestry of color and texture as they wave in the current together, it's almost like a symphony of textures. Just because you have found a sea turtle doesn't mean you're going to get spectacular film or pictures of a sea turtle. Everything is dependent on the activity, the light, and the angle of view. What are they doing? Are they swimming? Are they breathing? Are they feeding? If they're feeding, are they feeding away from you, or are they feeding slightly towards you so you see the entire texture of the shell, the beautiful flippers, and their mouths chomping on the seagrass? This morning I found a seamount in the middle of a lagoon. Sand and eelgrass, as far as you can see, and one coral head that came up in a beautiful cone shape. I got enamored with the fish that were in there for protection. The snappers and groupers and some of the little tiny squirrelfish, they're all kind of gravitating toward that seamount for protection, so I went for the fish. I realized that's not the story. The story is the entire biosphere of the seafloor going to the seamount, the surface of the water, and then all of the fish surrounding it. That's the shot. Here's our chance to enjoy some of the heroes from the ocean realm. One of the issues with all of the global coral reefs is die-off, and it's bleaching, and it is global warming and changing in the temperatures of the oceans. I choose to use my photography to stand with nature, our delicate planet, and the wildlife that are shown in this documentary. Imagine a world without coral reefs, turtles, whales, stingrays, and those are just the obvious animals at risk.
And think how these wild creatures have so much in common with each other and with us. Through Todd's lens, we see a vanishing natural world. We can see a world we have the power to protect. If we, of all creatures, can best understand consequences and plan far ahead, then let us do so. To the ends of the earth is sharing the earth's beauty to illustrate exactly what is at stake. Collectively, these photographs explore different aspects of the animal's behavior, a visual commentary on what it means to be born free into the last wild places.
The desire to discover new worlds has taken humans deep into outer space. But planet Earth still holds its own secrets, with much left to be discovered in its liquid depths.
The ocean covers 75% of the Earth. We don't know much about them.
We know about the surface of the Moon and Mars better than we know about the actual seafloor.
In Florida, reports of large gatherings of fish in the Gulf of Mexico piqued the interest of divers. They discovered an unlikely find beneath the fish. Deep, dark holes opening down into the seafloor.
You're swimming along on the bottom and it's very sandy. You'll see some fish go by, some random organisms around, but then you approach these holes and all of a sudden it's just booming with life.
These openings, commonly called blue holes, vary in size and depth. Some have only a small entrance that's 5 feet wide and opens up into a large room, while others extend down over 400 feet into the earth.
But the allure is, well, you wonder what's a little deeper and a little deeper. But pretty soon you're 150 feet or so, and there's more to see. So you want to go deeper and deeper and find out what's going on.
These environments are so understudied that we don't even have the basic information to just characterize them.
Now, multiple institutions and volunteer technical divers are teaming up for expeditions to explore these environments like never before.
It's definitely exotic. The ability to really get in these systems and make human observations, which is really important, is pretty analogous to space exploration.
Nobody's taken measurements. Nobody's looked at the fauna. Nobody's looked at the geology or where they float. It's all exploration.
We're interested in whether or not these holes are connected to mainland Florida. Is there any connection through the groundwater system? Is any of the fresh water getting out to these holes? If they are a source of nutrients, which could potentially be a possible source of nutrients for red tide. We don't know.
Why are these deep holes in the seafloor? And what makes them vibrant oases in an ocean desert? Florida is a state born from the sea. The peninsula sits on a foundation of porous Swiss cheese-like limestone, making it home to many springs, caves, and sinkholes. Highly trained divers from around the world explore these liquid labyrinths for a taste of adventure.
I had an interest in them, and I had been a diver for a long, long time. And I had been, since the mid-'70s, been diving in springs and sinkholes and caves on land.
Mote Marine Laboratories' Jim Coulter is part of a small percentage of divers that venture into the planet's intricate underground cave system. He first heard about similar features that existed offshore from fellow cave divers.
What if there were these offshore springs with fresh water? What kind of community would you have on those sites? And where would they come from?
Some experts believe these so-called blue holes may have formed over 10,000 years ago when sea levels were much lower, exposing a larger portion of the Florida shelf.
It rains, the water sinks in the ground and flows through this porous limestone. It will slowly dissolve the calcium carbonate and form these cracks and crevices. They'll start to form channels and little tunnels, and they might form caves and springs. And all the sinkhole basically is an underground cave that the ceiling collapses.
In 2005, Jim received a grant to begin to quantify and characterize the blue holes that fishermen had reported between 25 and 50 miles offshore.
So we would go out and try to find them. We'd dive in them to see how far they went, see how big they were.
Jim and a team of exploration divers verified over 20 different holes, all with diverse ecosystems, attracting Goliath grouper, schools of jack, turtles, and even whale sharks.
It's like this biological hotspot out in the middle of the Gulf of Mexico. What is causing these oases to be out there? You know, why do all these animals love being there?
To the server.
To learn more about these mysterious holes, a team of multidisciplinary experts joined forces in 2019. They began by exploring Amberjack Hole, a sinkhole located 30 miles off Sarasota. Amberjack Hole is found 114 feet below the surface and opens down to depths beyond 350 feet.
It's a little bit of a journey to get out to the hole. It takes a good 2 hours depending on which boat you're on. And once we're out there, the first thing we have to do is anchor the boats and make sure they're in place over the holes. We're working with citizen scientists. So we depend very heavily on tech divers to be able to accomplish this research. We need divers who are certified to go to extreme depths like 300, 400 feet.
It's a very different dive site from traditional diving. A lot of people have some apprehension just because it's this big black hole in the bottom when you go there.
Recreational divers are able to reach the opening of the hole at 114 feet on a single tank of air. But to get to the bottom of the hole, divers must prepare for a dive that will take up to 3 hours and that requires more gear. Technical divers also use a blend of gas containing oxygen, nitrogen, and helium called trimix to avoid the harmful effects of breathing air at depth.
You add helium to your mixture for 2 reasons. One, you want to get rid of as much nitrogen as possible because nitrogen is what causes nitrogen narcosis, which so it affects your rational facilities. You know, makes it a little harder to think straight underwater. Using trimix, you can remain lucid and can do your work. As a scientist, you can be more functional with deeper dives. The drawback, of course, when you go deeper is it just takes you much longer to get back to the surface. A little more risk involved.
The addition of helium also helps reduce the risks of oxygen toxicity and decompression illness that are potential threats during long, deep dives.
If you obey the rules and be careful, very good scientific tool that can be utilized for exploration.
How was it?
Nice. Not bad.
Scientists are visiting the site in the spring and the fall to record any potential changes between seasons. One of their objectives is to survey marine life in the area.
We have a contraption that's an underwater camera in PVC where we can take a video going along this transect. And so we do that around the rim, and we also do it vertically, going down into the hole. And then so we're seeing so far as we start swimming the transect.
A lot of sponges, a lot of those taller things are sponge. The orange encrusting are sponges. That's a colonial, the white things are colonial tunicates.
Experts later analyzed the video to identify the types of organisms found in and around the hole.
The first 20 or 30 feet below the rim is highly productive. It has a lot of sponges, there's corals. You see fishes and crabs and bivalves of different types. It's a very diverse area.
And then as you go down into the hole, the zones start getting less diverse and become more cold water tolerant, like lower light tolerant type organisms, and it just maybe perhaps even down to where it's just more microbial type organisms.
The videos show there is more sargassum in the spring versus the fall. Additionally, a strong green layer in the fall suggests higher levels of chlorophyll and nutrients around the rim.
You do both? Let's do both.
Scientists also collect water samples from the base of the hole up to the surface.
My main focus is looking at the chemistry and to see if it's providing anything extra to the surrounding water. Is it a nutrient source? Is it a sink? The Gulf of Mexico is a very oligotrophic system, meaning there's not a whole lot of nutrients just out there all the time. Just in our initial exploratory dives, we know that pH drops as you go into these holes. Temperature also drops, and we know that nutrients are elevated in these hole systems. And so we're trying to understand why, what's causing this.
While the nutrients may be attracting marine life, scientists worry they could also have a potentially adverse effect.
If it is a source of nutrients out in the middle of the Gulf, that would be really important, especially since we know that a lot of red tide blooms form offshore.
To determine if there is a link between these holes and red tide blooms, experts say more research is needed.
I'm setting up everything to check the lander.
Another group of experts from Georgia Tech and FAU Harbor Branch custom designed a high-tech device called a benthic lander, which surveys the sediment and water at the bottom of the hole.
The benthic lander looks like almost like the moon lander, something that we would put in space. It's also got a lot of instruments on it.
For this particular lander, we typically lower it on the seafloor from a crane on the ship.
In this case, with the hole being so narrow, it's a pretty small target. When you think about waves and things like that moving a ship around, the ship isn't really able to get the lander down there.
Since Amberjack Hole's diameter is only 75 feet, divers must guide the lander into the hole.
The lander weighs 400 or 500 pounds. So this thing sinks fast to the seafloor. We added flotation foam to it to make it completely neutrally buoyant so that the divers could physically maneuver it underwater and get it down into the hole.
That's something new that we had never tried before, so we're a little bit anxious about it. See if it's gonna work.
Technical divers can only stay at a depth of 300 feet for a short period of time, whereas the lander can continuously collect data over a 24-hour period. One component, called a benthic flux chamber, samples nutrients, carbon, and oxygen that transfer or flux in and out of the sediment.
Think about like taking a coffee can and inverting it on top of the sediments. Now you have a good little volume of water, and we have syringes that take samples from that little parcel of water every 4 hours, and they're sampling both inside the chamber and outside the chamber. Outside the chamber is sort of a reference, like a background. Inside the chamber tells us how much is actually coming from the sediments themselves.
And then also we have this electrochemical analyzer, we call it.
These electrodes actually allow us to monitor things like oxygen, sulfide, dissolved iron, dissolved manganese.
Once the experts determine the amount of nutrients and other elements accumulating inside the chamber, they can calculate the total amount of nutrients and other elements fluxing in and out of the sediment at the bottom of the hole. These measurements tell the scientists more about the microbial and chemical processes that occur in the sediments at different depths. To obtain additional information, Jim and volunteer technical divers also collect sediment cores.
So these are sediment samples. They came from the bottom of this particular hole at about 310 feet deep. And there's kind of what we call a debris pile on the bottom. This amount of sediment could represent, perhaps hundreds of years of sedimentation. Jordan will be looking at the chemistry of the sediment and see how it's functioning. And so we'll take it back and get it analyzed.
So we're going to put the reference.
One core is used for further electrochemical analysis, while a second core is sectioned to determine how levels of nutrients and other elements change with depth.
So we're pushing the mud out using a piston, and we section it in small intervals. We then spin it in a centrifuge for 10 or 20 minutes. We separate mud on the bottom, water on top. We pour that water off, and then we filter it. We can use these pore water samples and actually conduct our analyses.
Jordan and his lab run a variety of analyses, including measuring grain size, a necessary step to model how nutrients may be fluxing out of the sediment.
We want to know if it's clay, if it's sand, if it's silt. We want to know the actual distribution of the grains in the mud. How does it compare in the hole, and how does it compare out of the hole? The next measurement we do is organic carbon. We basically weigh the sediments before and after burning. We're measuring how much carbon, hydrogen, and oxygen is lost. It's just sort of a snapshot of how much food is there.
This carbon feeds microbes living in the sediment. Additional analysis of the sediment samples showed ammonium and phosphate found in the sediment increased dramatically with depth. These same nutrients also accumulated in the benthic flux chamber.
Usually when you see a profile like that, it means that you have a flux outward. Sure enough, the nutrient measurements show that the bottom water of the blue hole is enriched in ammonium. So we're almost certain that a large portion of this is coming from the sediments themselves.
These results signify intense microbial activity in the sediment, an unexpected finding.
It's like the blue hole itself is actually responsible for creating this ecological island. So now it's sort of a chicken or the egg problem, right? Because you have this hole, and because the hole forms a shelter for fish, you have a lot of fish living there. The fish excrete, the fish die, they deliver this organic carbon, it collects in this blue hole.
Microbes break down the organic carbon and then excrete more nutrients, which fertilize the phytoplankton at the surface above the hole, which creates food for animals higher up the food chain.
So this cycle is just sort of really sustained by the physical morphology, the geology of this blue hole.
a team of biologists from Georgia Tech is closely studying the microbial life inside the blue hole to see how it might differ from the surrounding ocean.
Yes, please. 54 surface. We're looking at both sediments from the bottom of the blue hole and water column samples from the bottom all the way up.
DNA analysis of these samples makes it possible to determine what species of microbes are present and what functional roles they play in the ecosystem.
We see some really interesting things about this blue hole. The oxygen is really, really low in the water column.
Okay, so let's plot graph.
Jordan found oxygen levels decreased dramatically to 10% just below the rim of the hole. They then briefly increase again at 260 feet before falling to zero just above the debris pile.
Okay, wow, those smell.
We noticed it was really sulfitic at the bottom. We could smell it in our water samples. The divers could smell it when they were down there.
Jordan's lab confirmed that the bottom of the hole is very high in sulfur content.
When there's no oxygen in the environment, microbes can get creative and use other types of chemicals to breathe. They're breathing sulfate and they're producing sulfide.
Hydrogen sulfide is a poisonous gas to most marine life that may become trapped in the blue hole and die.
So our communities from the water column are very different between the surface, middle, and deep layers. And they are represented by 3 distinct microbial communities. And this is really interesting to us. It means there's not a lot of mixing, means things are very stratified. We're trying to get better resolution so that we can tell where exactly that switch happens, and does it correspond to a switch in oxygen or in sulfide.
Nastasia and her team made another surprising discovery. Microbes called archaea make up almost 50% of the species living at the bottom of the blue hole. This incredibly rare finding could have implications for astrobiology.
If we're interested in life on other planets that don't have oxygen, how might things be living there? Maybe this microbe has enzymes that help it breathe without oxygen, and we're going to find that on a planet one day, and we'll know how these things are living because we have examples of microbes that are living that way here on Earth.
Much remains to be revealed about the mysterious blue holes in the Gulf of Mexico. One of the remaining uncertainties is if these blue holes connect to a larger underground network, and if that network connects to Florida's mainland.
And then the question, is it a static system or is it a moving system or is there some kind of exchange? That's where my part comes in.
We're going to take 2 samples within the blue hole and then 1 right at the rim.
To understand where the water in the hole is coming from and where it might be going, research geologist Chris Smith analyzes radioisotopes found in water samples.
The radioisotopes we're using are naturally occurring. They exist in geologic materials that make up our continental crust and oceanic crust. So what we hope to get an idea of whether or not there's movement of the water either from the aquifer matrix to the blue hole and or the movement of the water from the blue hole up into the overlying water column.
Chris pumps 50 liters of water over a fiber and collects water samples from hand-lowered bottles to analyze various radioisotopes. By knowing how long it takes for certain radioisotopes to decay, Chris can determine the relative age of the sampled water.
So it's kind of like an internal clock, and so we can use it to kind of measure how long it's been either moved away from its origin point or how long it's been in transit from some other location. In the open ocean, some of the first samples we collected, it was below our detection limit actually. It was so low. But at 60 meters below, we were picking up concentrations that were probably 100 to 1,000 times greater than our detection limit. And so there is that enrichment at those depths relative to the water that's sitting right at the surface.
Chris's findings suggest water is moving from the bottom of the blue hole to the overlying water column. But further investigation is needed to determine if there is any exchange of water with Florida's extensive underground geological matrix. Many secrets remain under the sea, but scientists are one step closer to understanding these enigmatic blue holes as ecological oases in the Gulf of Mexico.
The ocean is not just kind of the coastline and then a flat desert. You know, everything in between the coastlines is just boring and flat. And these blue holes are just one example of that.
I think it's important to better understand what's actually out there on the seafloor. It's really important for us to sort of establish, map out these conditions, unravel any sort of connections in establishing the environmental and ecological importance of these blue holes. By us going out here and taking these initial measurements, we may be able to justify future exploration.
Then we can take kind of this methodology that we're coming up with how to analyze these holes, how to characterize these holes, and bring that to other holes in the future, and maybe even to see if there's differences from the northern Gulf of Mexico to the southern Gulf of Mexico, or east to west.
People ask, what's the major discovery? What's the big finding? And as a scientist, you know that there's very few big deals that are found out all at once. Mostly it's a very slow process that builds on previous research, one little bit at a time. And the ultimate goal is to provide a better understanding of the big picture of how things work.
They are always out there.
At any one time, if you take a drop of water from anywhere in the oceans, you'll literally see hundreds of different species.
But sometimes, algae grow out of control.
What we're really concerned about is the frequency and the duration and the intensity of these blooms.
Harmful algal blooms have dominated the headlines.
What used to be isolated blooms are now becoming very, very common and widespread.
And they are affecting the ecosystem.
I think even just looking at our historic numbers, we saw higher numbers in our area of strandings this past year with both sea turtles and marine mammals.
But how are they impacting human health?
You can end up in the hospital for weeks.
And will they ever go away?
The one thing we do know is we seem to be seeing bigger and longer lasting blooms.
Algae are aquatic, plant-like organisms that include a broad range of species, from microscopic phytoplankton to large seaweeds. They are the energy producers of the sea.
At these low levels, they're a food source for other organisms. It's just at the high levels where we get blooms, where they become, if you will, killers.
When algae grow out of control, they can cause harmful algal blooms.
So harmful algal blooms are just occurrences of algae that have some kind of negative repercussion either to the environment or to humans, either human health, economy, tourism, things like that.
Harmful algal blooms have been reported in Florida since the time of the Spanish conquistadors.
What is changing now, these things occur naturally. These are algae that have existed in the oceans long before we even had societies as humans. They're starting to grow more frequently into these harmful algal blooms and spreading out where we see them in our waters. So what used to be isolated blooms are now becoming very, very common and widespread. So this is a problem.
Florida Atlantic University's Dr. Brian LaPointe is an algae specialist interested in how nutrient pollution affects algal blooms. To figure it out, he samples the macroalgae sargassum from his lab in the Florida Keys.
We have many, many species, but Sargassum natans and Sargassum fluitans are the only species that have adapted to this floating life on the ocean's surface.
A common sight in the tropical and subtropical ocean, sargassum mats are important for the ecosystem.
Sargassum in its natural state is a very positive thing. Sargassum that is floating on the ocean surface supports a diverse array of invertebrates and fishes that are associated with it. Some of these are endemic. In fact, they don't grow anywhere else.
But like any algae, sargassum can grow out of control, causing a harmful algal bloom.
What we've seen happen just since 2011 is what I call too much of a good thing.
These dramatic increases in sargassum growth are thought to be caused by increases in nutrients in the water.
We have some major river discharges, all carrying increasing nutrients to the coastal ocean, where they become available to sargassum. But other factors as well, such as atmospheric deposition, rainfall carrying increasing amounts of nitrate, for example, can be playing another major role in delivering more nitrogen to sargassum.
And while sargassum is not a toxic marine algae, coastal communities feel the negative impacts.
The infrastructure to deal with these excessive amounts of sargassum is just not there. We've never had to deal with this before. I hear from resorts around the Caribbean that are literally ready to shut down. They are powerless to do anything to deal with this problem. They've tried a variety of things to try to hold it off the beach, and that might work on certain days when the wind is low and the currents aren't strong, but ultimately forces of nature overcome.
One theory is that a sargassum bloom might trigger other kinds of algal blooms.
As the sargassum decomposes, it releases chemical compounds, including nutrients, that can become problematic.
Logically, anything that's going to fertilize the oceans and give a release of nutrients is a problem.
As part of his research, Dr. Malcolm McFarland regularly takes water samples from Florida's Indian River Lagoon.
So this is a device that takes a measurement that is very similar to what a satellite might see orbiting the Earth. It basically measures the color of the light that is reflected from the surface of the water back upwards. We generally sample once a week or every other week. It depends on what time of year it is. We like to keep tabs on what's going on out there. These are basically plants, so they require fertilizer just like land plants do. A lot of those nutrients come from agricultural runoff or sewage treatment plants, people's septic systems. All these sources are increasing the amount of nutrient pollution that is entering the lagoon and other coastal waters.
One species Dr. McFarland monitors for creates what is known as brown tide.
The brown tide refers to a species called Oreoumbra lagunensis, and this is especially abundant in the very northern parts of the Indian River Lagoon near Cape Canaveral.
Brown tide makes the water look like chocolate milk.
The water turns brown, dark brown. So at nighttime, they're actually using oxygen just like we do for respiration. They can draw down the oxygen in the water, and they can cause a fish kill. So all the other organisms that are in the water that need oxygen suddenly can't breathe, essentially.
It's an unusual species that a number of years ago was associated with deep open ocean environments, but it has found a niche within these coastal lagoons here in Florida and also over in Texas. It is a very small cell, so it's only a little bit bigger than most bacteria, but it gets incredibly abundant. As far as we know, it is not toxic. It has not been terribly well studied as some of the other organisms, like the red tide.
Red tide is another harmful algal bloom, one that does produce toxins. Severe red tide outbreaks have made headlines as fish, some as large as whale sharks, as well as sick or dead sea turtles and marine mammals, have washed up on shore.
Red tide generally refers to a bloom of a species called Karenia brevis. It's a type of dinoflagellate, which is a type of phytoplankton that is common throughout the world's oceans. And generally when it gets very abundant, it can discolor the water red, hence the name red tide.
It's a really interesting creature. It has animal-like characteristics and it has plant-like characteristics. The animal-like characteristics is that it has a couple flagella and it can actually swim up to the surface. The plant-like characteristics are that it photosynthesizes. So it's in one of these unique categories that have a little mix of both.
Karenia brevis is particularly bad, produces a toxin called brevetoxin. That's where the brevis name comes from. It is a neurotoxin.
Red tides are a regular occurrence off the Florida coast.
Florida gets them pretty close to annually. Now people will kind of scratch their heads at that and say, oh, I remember such and such a year we didn't have any dead fish on the beach. Sometimes the way the physical oceanography works, there's a red tide perhaps sitting 10 miles offshore, but the currents are such that they don't get pushed onshore.
In 2017, there was a severe red tide outbreak off the west coast of Florida. The extensive bloom lasted nearly a year and a half, even making its way to the east coast of Florida for a few months, which is a rare occurrence.
It got advected over, most likely through the Florida current and up through the Gulf Stream, up into the east coast area of Florida. We hope that that is not a harbinger of what may happen in the future, that the blooms on the west coast are getting bigger and more persistent, and because of that, their chances of getting moved over to the east coast are now going to go up, and that the east coast may start seeing these same kind of effects year after year.
During that same outbreak, Dr. Monica Lara conducted regular reef monitoring with her students on the rocky reefs off the west coast of Florida.
About a couple of weeks after we believe the red tide came through on some of those reefs, we did go out and dive, and it was a dramatic difference. There were very few fish. The invertebrates were still there, but there were some bivalves that were dead all over the place.
One of the theories, and that's all it is a theory, is that red tide released the toxin. The toxin gets in the water, goes across the gill slits of fish. Again, it's a neurotoxin, so it affects the central nervous system, and the fish quit breathing, kills the fish.
The reef was silent. It's like the sounds from the animals were completely gone. So it was like a desert, a silent desert. It was really, really dramatic.
Once the dead fish begin to wash up on shore during a red tide event, many birds start to feed on them.
Early signs of a red tide and the seabirds is kind of staggering drunk behavior, or they won't be able to stand or walk, kind of be placed on the ground just sitting there. It really affects their neurological system, so they're kind of hopeless until somebody picks them up or they die.
Rescue groups say seabirds of all sizes were affected by the red tide outbreak.
We actually see the smaller birds like the ruddy turnstones and the sanderlings first. They are kind of our canary in the coal mine. We'll see them immediately, and then we start getting the bigger species like the laughing gulls and the double-crested cormorants.
Seabirds are impacted not only from eating poisoned fish, but also from swimming through bloom-filled waters and inhaling the brevetoxin. With fluid therapy, the stronger birds are able to expel the toxins and recover.
We release about 3/4 of the sick birds, which for being such a bad red tide was really good.
During this severe bloom, rescue missions were also underway at neighboring Mote Marine Laboratory.
We had extremely elevated numbers of strandings. We've recovered over 300 sea turtles this year, over 30 dolphins, assisted with countless manatee recoveries and rescues.
Marine animals are affected by the brevetoxin in different ways.
So for our sea turtles, they generally get it through their food, and it's a neurotoxin. They get really disoriented. They have a hard time surfacing and clearing to get air. So a lot of the carcasses we were recovering had, indications of drowning. If we can get to the animals in time, we can get them help. But unfortunately, there aren't people out there to see them. Similarly for the manatees, it's also a neurotoxin. They get that through their airways when they're breathing. And much like the turtles, if we can get to them in time, they can come out of it. We've had animals that we're holding their head because they won't even surface to breathe. As we hold their head and they're breathing a little bit fresher air that's not right at the air-water interface, they can come out of it. And they can metabolize that toxin and actually leave while we're waiting for the rescue trucks to get there. So it's, those are always sort of interesting cases. And for the dolphins, we don't have a great handle. We know they get it through their food, but we haven't had any live dolphins to respond to. We know it kills them because we've recovered many carcasses, and most of the animals that we've tested from the summer have been positive for brevetoxin at high levels. So, we know that's an acute cause of stranding, but I don't know how it affects them when they're alive.
Humans are also vulnerable to red tide, since it can aerosolize and its toxic particles can be breathed in.
A certain subgroup of humans are very susceptible to breathing the airborne toxins. And in particular, asthmatics need to be very careful when there's a red tide in town to not be exposed to the toxins. The good news is everybody reacts to the toxin. And when you inhale it, you get a dry cough, you get nasal congestion, you get eye tearing. And why I say that's good is that you're getting exposed. It's not like something like radon that you have no knowledge of. So the important message is don't avoid the beach, but know what beaches are impacted and what beaches are okay.
Brevetoxin likely becomes airborne through wave action. Humans can also get sick from consuming fish or other seafood that have been exposed to red tide.
Fish consume the toxin, and the toxin accumulates in the guts of the fish. So if we fish during a red tide and you fillet it, you won't get sick from any potential toxin because of the toxins in the guts of the fish. We do need to educate people. There are some cultures who consume whole fish soup, and so they need to know that during red tides, you can't throw the whole fish in there. Your family potentially can get sick.
The causes of red tide blooms still aren't clear, although it is thought that there has to be a perfect mix of temperature, oceanic conditions, and nutrients.
During certain years, the conditions seem right, that there's some kind of a nutrient that is added to the system, and so then they're able to increase in numbers. What that nutrient is, we're not sure.
Whatever that nutrient is, some experts say humans likely introduced it into the oceans.
Average abundance of red tide on the west coast now is about 15 times more than it was 50 years ago. To generate 15 times more red tide, you need 15 times more nutrients. And I can't think of any natural sources of nutrients that have increased 15-fold. But of course, what has increased dramatically here in South Florida over the last 50 years is number of people, agricultural interest, and so on. We're just driving along the northern side of the Caloosahatchee River, sampling at various locations along there. Right, we just finished sampling the Artono Lock. It's one of 3 dams and locks on the Caloosahatchee River, and now we're heading over to the west coast.
Red tide isn't the only algal bloom that's been wreaking serious havoc in Florida waterways in recent years. Dr. Larry Brand has been sampling for cyanobacteria in the waters around Lake Okeechobee and in the Caloosahatchee River for almost 20 years.
Well, there's a lot of changes. I can't really say for sure there's been a long-term change over the past 20 years, but certainly some years you have really bad blooms of cyanobacteria, and some years you have less so. But it's very clear that these are very nutrient-rich waters, and you often do get these large blooms of cyanobacteria.
When water levels in Florida's Lake Okeechobee get too high, flood managers, fearing a breach in the dikes surrounding the lake, discharge billions of gallons of water through canals, rivers, and streams into the Gulf of Mexico and the Atlantic Ocean. This can bring nutrients which have built up in Lake Okeechobee to the estuaries, causing these algal blooms.
The cyanobacteria tend to do better in warmer weather, so we tend to get these blooms primarily in the summertime. Of course, it's also in the summertime because that's when you have more rainfall here in South Florida. That's the wet season. So you get a lot more land runoff. And of course, that's the source of most of the nutrients in Lake Okeechobee and the Coosatch River. Various nutrient sources on land, and then during the wet season, all that rainwater flushing those nutrients into the water bodies.
Cyanobacteria are also known as blue-green algae. They were some of the first organisms on Earth.
They're really tough. It's really hard to kill them. And we now know they produce a lot of pretty nasty toxins. And they also produce over 1,000 other compounds which simply have not been characterized yet. We have no idea what the health hazards may be when you're exposed to these blooms. But some of the best known ones are for microcystin. That can lead to long-term liver damage and even liver cancer. And more recently, we've discovered a compound called BMAA, and there's increasing evidence, pretty good evidence now, that it can lead to neurodegenerative diseases like Alzheimer's, Parkinson's, and ALS.
Blooms of cyanobacteria are characteristically bright green and can be as thick as guacamole.
Every time I travel along the Coosatch River here or along the shores of Lake Okeechobee, I see people fishing. I know there's high concentrations of BMAA in these fish and probably also microcystin. I certainly will not eat the fish in this river, but I do see people doing so. And there's no signs along any of these water bodies warning people about the presence of these toxins.
Experts say the biggest question now is whether cyanobacteria pose an even bigger, more silent threat than we know.
Well, right now what we're focusing on is the possibility of the toxins in these blooms of cyanobacteria getting into the air. Now for the red tide offshore, it's been known for a long time that that toxin gets into the air because it has immediate effects on people's eyes, nose, throat. I call that a good toxin in that you know right away you're being exposed to it, so you can do something about it. But these toxins here in these blooms of cyanobacteria, like microcystin and BMAA, microcystin can have short-term effects, but the BMAA has no short-term effects. It only has long-term effects. If that toxin is getting into the air, if you live near this river or some of these other water bodies that get frequent blooms of cyanobacteria, you could be breathing in this BMAA, not know it, and then 10 or 20 years from now you could come down with Alzheimer's. So that's a much more insidious toxin.
To determine if cyanobacteria can become airborne, a multidisciplinary team at the University of Miami is working with Dr. Brand's water samples. The team designed a wave tank to create conditions like those at Lake Okeechobee.
We have a wind wave tank set up in order to blow air and create more realistic conditions for the transfer of the aerosols across the air-sea interface. So we're going to create this condition where the wind's blowing over the water surface and see what's produced.
My lab does real-time techniques to measure the size as well as the composition of these particles. But if we want to quantify their toxins, what we do is we collect the particles on a filter, and then Dr. Poppendorf's lab extracts the material off of the filter and uses her mass spectrometer to quantify the toxins and also figure out which toxins are present in the samples. So the two techniques are really complementary for understanding the impacts of these particles on human health.
This project is in its early stages, so the results are still unknown. But one researcher from the medical school is already anticipating some interesting results.
My lab studies neurological diseases, including neurodegenerative diseases, and we use fruit fly as a model.
After exposing some flies to cyanobacteria from Lake Okeechobee blown through a bubbler for an hour, Dr. Grace Zai noticed some differences in the fly's behavior.
So there are several behavior tests we can to look at their nervous system function. And so first one and most commonly used one is called a climbing behavior. So what you can see actually is normally flies would climb up. If I flip this, all the flies started to climb upwards. This is the first time we're running this experiment. So we can already see an immediate difference between these two groups. So this one hasn't been exposed. This one has been exposed to the aerosolized particle for 1 hour. So can you tell which one is faster?
Not all toxins found in nature are necessarily bad. One of Dr. John Berry's missions is to identify new compounds in harmful algal blooms that may actually be beneficial to humans. In one experiment, he tests toxins he extracted from cyanobacteria on cancer cells.
We pulled out compounds that people just, they're not on the radar yet, and that's the idea, is to get some of these new potential toxins on the radar so that we can start to understand if they're having an effect. They've been a real gold mine for people looking for biologically active natural products for drug leads. So they're sort of these toxin/drug producing little factories out there in nature.
Florida has been hit hard, with multiple algal blooms negatively impacting the environment, human health, and the economy. The length and severity of these blooms is getting worse. People living along Florida's biggest waterways are clamoring for help in putting an end to the blooms.
And there are a number of people who are starting to hypothesize that we've hit a tipping point, that the combination of climate change and the patterns of rainfall and warmer waters that we've gone through, combined with all the development and land use practices that we're doing around our coastlines and the nutrient pollution that we're putting into our waterways, has put the systems into a very bad position, that they're irreparably harmed, that we're not going to get them back. I don't fundamentally believe that. I do believe if we can get a control on nutrient pollution, nature will fix itself. Nature is very resilient. It just needs time to recover. If we keep on beating it and polluting it, it's never going to recover. And yes, we'll be living with this forever.
April 20th, 2010. 41 miles off the Louisiana coast, the Deepwater Horizon drilling rig, leased by BP, suffered a devastating blowout and exploded in the Gulf of Mexico.
It was a very chaotic time. 11 people lost their lives, many others were injured. It was catastrophic.
Deepwater was probably the most complex and diverse oil spill in the history of oil spills. People were very prepared for another Exxon Valdez. They weren't prepared for this.
While the Coast Guard searched for survivors from the air, response teams worked to contain the fire at the surface. But in the deep sea, nearly a mile beneath the rig, the largest offshore oil spill on record was just getting started.
The first time I saw a video of the discharging wellhead, it literally took my breath away. I realized how truly bad this was and how difficult it was going to be to stop the disaster that was unfolding.
Turn speeds are posted. Number 1 inch. I've got gear up.
Over the next 87 days, BP's Macondo wellhead discharged roughly 134 million gallons of oil into the Gulf of Mexico. The unprecedented spill affected nearly 68,000 square miles of ocean surface and damaged 1,300 miles of shoreline across 5 states. Despite months of cleanup efforts, the spill became one of the largest environmental catastrophes in American history.
I knew pretty early on that this was going to be a marathon, a sprint. It was one of the most intense periods of my scientific life.
As a result of the developing spill, the Gulf of Mexico Research Initiative, or GOMRI, was created with a $500 million grant from BP for peer-reviewed, independent research on the impacts of the Deepwater Horizon disaster.
The Gulf of Mexico Research Initiative just transformed our knowledge of the Gulf of Mexico.
We started with a clean whiteboard to try to understand what we thought would be important 10 years from that point. So what we have to know to have a better response to it.
Yeah, there's a lot going on here.
Wow.
What was the extent of Deepwater Horizon's damage to ecosystems deep in the Gulf of Mexico? And are we prepared for the next big spill? Dr. Eric Cordes, a professor at Temple University, has been studying deep-sea corals for more than 2 decades.
They're not limited to shallow water. They're everywhere. They're in the Gulf of Mexico. We took a core through one of them and aged them at over 300,000 years. So these are structures that are living at geological scales.
Look at that. Beautiful.
These corals support biodiverse life in the deep ocean, providing nurseries, feeding grounds, and protection from predators. Some of the most productive fisheries in the world depend on them. Life-saving pharmaceuticals for diseases like cancer have also been developed from these corals.
Every one of those species is doing something different. So if you lose one, you may be losing something really important to us that won't evolve again.
Main deck control van, Bowers is coming in 5.
After the Deepwater Horizon disaster, Eric's work turned toward the spill's devastating effects on the deep corals in the Gulf of Mexico. As a principal investigator for the GOMRI-funded group EcoGig, he returned to the spill site.
We're proceeding at a half a knot right now.
Roger that.
His focus was on Paramaricia, the coral species most impacted by the spill.
Some of the colonies that were impacted were as old as 600 years. They grow very, very slowly, which sets up the possibility that it would take that long to recover.
Eric says the impacts researchers found on the seafloor near the site were shocking.
First corals we found, it was very obvious what was happening. There was oil covering it. There was tissue falling off of the skeleton. It was essentially rotting away in front of our eyes. Eventually, entire branches started to fall off. The Dirty Blizzard event actually transported a lot of the hydrocarbons and dispersants from the surface down to the deep sea very rapidly. And we would see patches of impact all over the place where they looked like they were hit with a shotgun. I honestly didn't think that that kind of thing would happen.
To better understand these impacts, Doctors Stephen Morosky and David Hollander at the University of South Florida have closely studied what became known as the Dirty Blizzard for the past decade. As leaders of the GOMRI-funded Sea Image, their focus is on the fate of Deepwater Horizon oil.
It's a very complex set of circumstances that results in large quantities of oil from an oil spill actually reaching the bottom. The oil globules and droplets, they float. And as long as they're above a certain critical diameter, they'll come to the sea surface.
At the surface of the oil slick, responders deployed nearly 1 million gallons of dispersants to keep the oil from moving toward fragile coastlines.
Dispersants are like hand soap. The general theory is that when applied to the surface, under wave action, it's sort of like washing your clothes. You know, you add the detergent, you've got the agitation, right? It creates the small droplets.
And so it doesn't make the oil disappear. It can make it more soluble. It can make the droplets smaller. It's not some miraculous wonder drug that removes it from the system.
At the Deepwater Horizon site, however, researchers observed unexpected impacts. The dispersants put so much stress on floating plankton and algae that they released streams of sticky mucus into the water.
That is like a glue that puts not only the oil droplets, but the dead plankton and the fine particulate matter together in large globules, which actually are heavier than seawater, so it sinks.
This sticky mixture of oil, dispersant, dead plankton, and other particles cascaded from the surface deep into the sea, blanketing the ocean floor like a dirty blizzard. Organisms that couldn't get out of the way suffocated.
There was a trade-off involved, and I guess the concept was out of sight, out of mind. And you push it offshore and you're free and clear. But that turned out to be not the case.
The oil and the dispersants are a toxic mixture, right? And so by having all that oil deposited on the sea bottom, it's going to interact with all the creatures that live at the surface of the sediment and also the creatures that live in the sediment. And so that created a lot of mortality.
Okay, here it comes.
It's estimated that up to 30% of the oil spilled ended up in the deep sea, contaminating vast areas of corals.
These corals are feeding on all the food that's raining down from the surface waters. So when this came down, they were thinking they were getting this big burst of food. A lot of it was consumed, and that caused a lot of the impacts that were observed.
As part of EcoGig's work to document the impacts of the spill, experts created a photo series of specific coral colonies over time.
So even after the oil disappeared off of the corals, we could still recognize that impact, recognize what those colonies looked like years later. And that allowed us to find additional sites where we could conclusively find impacts from the spill. Unfortunately, that time series that we've been following, all those corals that were impacted during the spill, we haven't had a chance to get back there in a few years just because of the lack of funding, which is, it's a shame because it's an amazing data set and we've learned so much from it. You never get those kinds of data in the deep sea.
In the Cordes lab at Temple University, Eric's team has attempted to reproduce the impact they saw at their research sites with coral samples that had not been exposed to the Deepwater event.
We're really interested in how the corals were actually dealing with the oil and dispersant exposure. So we brought some of the healthy colonies from one of our control sites that was far away from the spill. We collected some of them and we ran experiments exposing them to oil and dispersant at different concentrations. So we could really tease apart which one caused more damage and how exactly that damage was caused. We found that by itself, the oil actually wasn't that bad, but when we added the dispersant with the oil or the dispersant by itself, we saw more severe impacts.
The work that they've done with corals in the Deepwater has been incredibly important because, you know, these animals respond to dispersants in many ways the way microorganisms do. They're also stressed. Eric's work provided a window into impact that I don't think existed prior to their efforts.
As the project director for the EcoGig Consortium, Dr. Samantha Joy's research into the impacts of the Deepwater oil spill has also spanned the last decade. Her intense focus on the fate of the oil has led to questions about the effects of the dispersants on the very bacteria they're meant to assist.
The general idea of dispersants is that it's breaking the oil up, and then those droplets with their high surface area are accessible to these oil-degrading microorganisms, and it should be a feast for them. The best thing that can happen to oil is for a bacteria to chew it up, consume it, convert it to CO2, get it out of the system. It's not dangerous anymore. And that would be fantastic if that's what happened. But it's not clear that that's what happens.
In her lab at the University of Georgia, Mandy and her team have worked to recreate the same conditions and results seen with the Deepwater Horizon oil spill. Mandy's team measured the response over time of bacteria in seawater by adding differing combinations of dissolved oil and dispersant, which allowed the team to distinguish between the effects of the oil and dispersant together and also each substance on its own.
And by doing that, we saw the highest rates of oil degradation were in the presence of oil alone, and that when you added dispersants in with the oil, you reduce the potential for biodegradation, and that's a really important finding.
The results of Mandy's initial experiments led to an even more striking discovery.
There was something about the presence of nutrients, dispersants, and oil that seemed to maybe stimulate oil degradation a little bit. So we did a couple of different experiments aimed at isolating the effect of dispersants and nutrients. And we did this with surface water collected near the Deepwater Horizon wellhead. And when we did these experiments, I was astonished.
In cases where the nutrients were added, Mandy says the microbes were more effective at degrading the oil. Where the nutrients were limited, the microbes were more stressed, and the rate of biodegradation plummeted. Adding dispersants only stressed the microbes further.
All communities on Earth are stressed by something, whether it's hot or cold or pH or light. Then if you stress them further by exposing them to detergents, for example, that's going to be a double negative. They've been punched once because they're nutrient limited, and now you're punching them again by exposing them to a dispersant.
Mandy says her team's discovery about the impact of nutrient levels on the effectiveness of dispersant could potentially change future oil spill response.
If you can predict the result that you see based on the nutrient content, you've got predictive capacity. You can make a better judgment in terms of whether or not you should apply dispersants, because sometimes adding nutrients alone might be a good solution. By applying nutrients, you're increasing the fitness of this population, and by increasing their fitness, they're able to endure and tolerate what would otherwise be something that is an inhibitory stressor.
Mandy's findings may also solve a different kind of scientific problem. In many studies on dispersant effectiveness, there have been a wide range of results. She says her nutrient discovery suggests that the way experiments are being conducted is the determining factor.
Everybody's getting an answer that is reflective of the status of the system they're studying. It really sort of takes away this cloud of you're right and I'm wrong, and it turns that into a spectrum of responses, and it changes the conversation completely. And from one that's antagonistic to one that is very cooperative and synergistic, and we can all sort of figure out, okay, let's figure out the best thing to do for this ecosystem without impacting the system in a negative way. And really, that's what everybody wants to do. We've just gone about it in different ways. And that's the conversation changer. It's not right or wrong, it's how can we make them most effective?
Let's spray on.
Some members of the scientific community say Mandy's groundbreaking research calls into question the wide application of dispersants without first understanding and assessing their full impacts.
We done? We're done.
This is one of the tried and true approaches to oil spill remediation, and that can have a negative effect to the system, to the biology, to the ecology as an ecosystem, and to basically all the environments from the marsh systems down to the bottom of the sea.
One of the many unprecedented aspects of the Deepwater Horizon oil spill was the application of more than 750,000 gallons of surface dispersants at the wellhead below.
What we're seeing here is sort of a wand of dispersant trying to be added into the rising oil and gas, exploding petroleum coming out of the wellhead. The argument was, if we applied dispersants in the subsurface, we should be able to mitigate all oil coming to the surface.
In the early days of the Deepwater disaster, oil evaporating at the surface made the air above the site toxic, forcing responders to wear respirators while they worked to contain the spill.
That was the underlying justification to do this. And again, it was experimental because nobody had ever tried it before, which is a reasonable thing to do if it works.
But research conducted since then has called this subsea dispersant injection into question. At the time of the Deepwater Horizon blowout, Dr. Claire Paris at the University of Miami had developed open-source computer modeling of the ocean systems to trace the transport of particles and movement of fish larvae. She received a grant to modify her models and trace the paths of oil droplets from the wellhead instead.
I started building this model where now I didn't have particles anymore, I had droplets, and it was reading the temperature and the salinity of the ocean circulation model to change the buoyancy of the droplets, so it was completely connected with the ocean. I remember the first time we ran the simulation and we saw Actually, the droplets rise in 3 dimensions. It was amazing. I couldn't believe it. We could actually do that.
Claire's oil transport and fate model accounts for varying ocean temperatures, salinity, currents, circulation, topography, depth, and pressure changes, and even the effect of wind at the ocean's surface.
The modeling is really intense calculations, and so to do that we use supercomputers from the Center of Computational Science of the University of Miami, because we have to release so many oil droplets. We release 10,000 particles every 2 hours for, in this case it was 86 days, but then after the spill is done, we need to continue to track the whereabouts of the oil.
Claire says her modeling of the oil droplets from the spill resulted in a surprising discovery. The addition of subsurface dispersant was unnecessary in deep water because the oil is dispersed naturally on its own.
The deeper the wellhead is, the more compressed the gas, and when it opens and there's a difference of pressure, it's like a bomb that explodes because it's sudden change of pressure, and the gas suddenly expands and atomizes the oil in droplets. And so what we saw immediately was that the small droplets never rose.
Claire's model showed that smaller droplets accumulated instead at depth, predicting the presence of a massive underwater plume of oil, which was later confirmed by researchers at the site.
Early modeling research had said that this might be a possibility with a deep blowout, but nobody had ever demonstrated this before. So those deep plumes were forming in the absence of the use of dispersants, and that's a critical piece of information when we talk about the relative importance of the dispersants versus the natural processes, because if they're forming, and they're forming in mass, and they're extending over tens of kilometers, then that means that the natural processes have to be very significant.
This was basically just spitting in the wind, literally. And so I think during the Deepwater Horizon event, it was wishful thinking to believe that subsurface dispersants actually played a role in mitigating the oil distribution.
So it begs the question, do we really need to apply millions and millions of gallons of dispersants at the wellhead to get the same effect?
While deeper wells may naturally disperse oil more effectively, some researchers suggest that the implications of depth for future accidents are sobering. With the BP spill resulting in $61 billion in total costs and damages, a more disastrous spill looms as a frightening possibility.
The oil industry is heading to the center of the Gulf in extremely deep water. Deepwater Horizon was at a mile. There are many oil wells out there that are 2 miles and deeper, and so that's becoming farther and farther offshore. In 2017, for the first time, more oil was produced in what we call ultra-deep wells than in shallow wells. Ultra-deep are 1,500 meters, or basically a mile deep and deeper, and that trend is accelerating.
And that's a wholesale change in the industry. And the question is, have regulations kept up with those changes? Are they better prepared in the event of a blowout or of a large-scale oil spill? And I think many would submit, no, they're not.
There's a direct relationship between the depth of the facility and the frequency of accidents. All right, so this includes not only things like unconstrained blowouts, but it also includes worker injuries and other things. It's just a much more challenging environment.
As you go deeper and deeper, the enticement is that the wells flow faster because they're under higher pressure, so you get a much higher yield on your effort. But that's also going to mean how do you put that genie back in the bottle if it gets loose? It took 87 days to cap the Deepwater Horizon wellhead. Imagine a situation in 3,500 meters of water. It's a nightmare scenario.
Nature is amazing.
The past decade of GOMRI-funded research into the impacts of BP's Deepwater Horizon disaster have resulted in vast amounts of new data and valuable knowledge. However, researchers warn that the next blowout will not be a carbon copy of the 2010 accident.
Chances are it's not. As a matter of fact, statistically, from an actuarial point of view, the chance is 0. So we can't use the past to fight the next war. We have to be prepared to think out of the box.
How do we actually get ahead of the curve here? How do you plan for everything when your mental model is something that occurred in the past?
Now we know where it went. It's not out of sight, out of mind. There is a cost. It may be valued in dollars, but it could be valued in completely different ways.
We have to take everything that we have learned, make sure that policymakers and responders are aware so that we can nip problems in the bud and be as effective as possible.
And now our expansion of drilling in the deep ocean makes it almost inevitable that there'll be another accident. There's no good environmental impact assessment for things like that. The only way to not have those impacts is to not be doing those things.
How badly do we need that oil? You know, I mean, we really should be moving off an oil-based economy and into renewables anyway. And so do we have to find every drop of oil in every sensitive habitat on Earth, right? At some point, it becomes not worth it.
Over 95% of all the living space on this planet is in the deep sea. But we're still discovering entire ecosystems that we didn't know of before.
We're going to screw up a system we don't even know about. And we're going to, in retrospect, we're going to say, geez, you know, why didn't we think about this?